Last time, we got plasma to fusion temperatures. Great, now what? This is the first episode where we stop thinking like physicists and start thinking like engineers. Today, we're taking a tour through the reactor core. Here's an overview so you know where everything is. At the center, we have the plasma. Directly facing it is the first wall. Behind that is the blanket. Surrounding those components is the vacuum vessel, with the magnets farther outside. And at the bottom of the chamber is the divertor. Up until now, we've mostly talked about producing, heating, and confining the plasma, but we haven't talked much about the systems that surround the plasma and survive what it produces. Let's start from the inside and work our way out. First, the first wall. The first wall is exactly what it sounds like, the first surface that the plasma sees. In a machine like ITER, it's actually the plasma-facing surface of the blanket modules. It has to survive intense heat and particle bombardment, while also being actively cooled. So pretty straightforward for fusion engineering. ITER originally planned to use beryllium armor for most of its first wall, but its updated design uses tungsten instead. Other reactor designs might use different material choices in the future too, as these materials are still a major area of research. But the first wall is only the surface, literally. Most of the energy from deuterium-tritium fusion is carried by the neutrons, and those neutrons go deeper into the reactor. That brings us to the blanket. The blanket surrounds the entire plasma chamber, and it's probably one of the hardest pieces of modern fusion engineering. It has several jobs. First, it absorbs energy from high-speed neutrons produced by fusion. Second, it shields the vacuum vessel, superconducting magnets, and other equipment from neutron radiation. Third, it transfers the resulting heat into the cooling blanket. And in a fusion power plant in the future, it also needs to breed tritium. Fire segue. Fusion consumes tritium, and that stuff is rare. Conveniently though, the reactor is already producing a source of high energy neutrons. If those neutrons interact with lithium inside of a breeding blanket, nuclear reactions can produce helium and new tritium. Not only does the blanket capture energy, it also produces new fuel for the reactor. Basically, today's fusion reactors would create tomorrow's tritium. ITER itself will receive tritium from outside sources, but it's designed to test several test blanket modules. These experiments should help determine how future reactors can become tritium self-sufficient. Behind the blanket is the vacuum vessel. This is the large sealed steel structure that actually maintains the high vacuum environment around the plasma. It also supports components like the blanket and divertor, provides additional radiation shielding, and acts as a primary confinement barrier for radioactive material. And outside of the vessel are the magnets we talked about in episode 3, creating the magnetic fields that confine and shape the plasma. But there's still one major part of the reactor that doesn't fit neatly into this inside to outside tour. Unfortunately, not everything in the plasma stays useful forever. Fusion creates helium ions, and over time that helium ash, along with impurities and excess heat from the plasma edge, needs to go somewhere. That's the job of the divertor. The divertor sits at the bottom of the vacuum vessel and acts as the reactor's exhaust system. Magnetic field lines guide edge particles towards it, allowing it to remove helium ash and other impurities that otherwise cool and contaminate the plasma. It also handles some of the most extreme heat surface loads anywhere in the machine. ITER expects its divertor targets to withstand roughly 10 to 20 megawatts of heat per square meter. So once again, pretty straightforward. Let's put everything back together. At the center, the plasma produces fusion reactions and high energy neutrons. The first wall faces the plasma and handles surface heat and particle loads. The blanket captures neutron energy, shields the rest of the machine, transfers heat to coolant, and in a future reactor, breathes tritium. The vacuum vessel maintains the vacuum and supports the components inside of it. The divertor removes helium ash, impurities, and excess heat, and the magnets keep the plasma confined inside the tokamak. Now we have a reactor producing a ton of heat, and we still haven't generated a single watt of electricity. Next week, we'll finally build the complete fusion power plant. That video will be linked here once it's out. Feel free to leave any questions down in the comments, and please like and subscribe while you're down there. Anyway, why are you still here? Click the next video.